Good afternoon. On a dreary, rainy Friday afternoon, we could have 3 feet of snow here too, so maybe that's the better choice we have. At least we are dry inside here. So the last time we talked about polymerization and we talked about isomers, and that there were isomers that were structural isomers, which have the same number of bonds, the same kinds of bonds, the same atoms, but they assemble differently to a different molecule. They have the same molecular mass, but they are very different atoms, and I gave you very different molecules. These are structural isomers. This, for example, is ethanol. It has 2 carbons, 6 hydrogens, and 1 oxygen. And this is dimethyl ether. This has the same number of hydrogens, 6, 2 carbons, and 1 oxygen, and the same kind of bonds. We didn't do double bonding or ring formation. And with this, we have a very, very different molecule, but it is isomeric. It has an isomeric structure. It's a structural isomer. The ethanol is a structural isomer of dimethyl ether. These are very, very strong differences. They behave very, very different. But then we have some more subtle differences, and this is represented with stereoisomers. Stereoisomers are isomers that have very subtle differences. And so far, you have here this ethylene dichloride here. So this is 2 carbons, and one has a hydrogen and a chlorine, and the other one has a hydrogen and a chlorine. And if we compare this here, this is also 2 carbons with a double bond. One has a hydrogen, and one has a chlorine bound. One has a hydrogen, and one has a chlorine bound. The only difference is that sterically, in space, they are in the trans form, so they are cross from each other through the molecule, and they are in the cis form. Cis means on the same side, okay? So these are stereoisomers, and it's not a whole lot of difference. Of course, there's a difference, somewhat also chemical difference at times, but it's not quite as pronounced as structural isomers. But you could also have, to this one or to this one, you could have a structural isomer, which would be that one. There you have a different arrangement of the molecule, of the atoms. You have 2 carbons and the double bond. This is fine. This is the same. But then you have the chlorine on one side and the hydrogen on the other side. So this has very different chemical behavior, and this is now, again, these are structural isomers. We then talked a little bit more about isomers as they relate to biological systems. And in order to do so, I had to explain to you there is one especially subtle difference between molecules, and this is called chirality. Chirality, means in Greek hand. So this is a handedness of these molecules. And chiral molecules, they are mirror images of each other. And they are not superimposable to each other. I've shown that to you. If you look at here, for example, at this non-superimposable mirror image, this is the mirror image of this one here. And I've shown this to you with a model where you have this chiral center, and then you have 1, 2, 3, 4 different, in this case, you have molecules there, all right? But sometimes it's a bit more tricky. Sometimes you have to have a much closer look, and it's not just the molecule, it's the whole group on a side that binds to the central atom, okay? So 4 different things, then you have a chiral atom, or chiral atoms, now a chiral center, and these are then, what are they called? They're called chiral isomers, and they are mixtures. So there is the probability, if you have a chemical synthesis, for example, to make a drug like alanine, you use alanine, you synthesize proteins from amino acids. And actually, synthesis of amino acids of proteins in our body only uses L-type amino acids. So L means lexarotary, and D means dextrorotary. That means left and right. That's also, I think it's from Latin. And this was discovered that there are two similar looking molecules that turn the light. If you separate them, the one turns the light in the left direction. If you shine light on it and then twist the light, okay? And the other one shines it, twists it into the right direction. That's why this L and D comes. And so this is a chiral molecule, for example. The chiral center is here. And there you have not the same kind of atoms, but you have a different kind of atoms. You have different kind of groups. Look at this. If you look at this carbon here, you would say it has a hydrogen here, it has a nitrogen here, and it has a carbon here, and a carbon here. And you would say this is not chiral because it has not 4 different things. But this is wrong. Look at it again. You have the carbon here. Now you have here a CH3 group, okay? This is different. Here you have a hydrogen. Here you have a CO2 group. And here you have an NO3 group, NH3 group, okay? So these are 3 different coordination partners, okay? Binding partners. And this is the chiral center in this, so it's not quite as clear-cut that you just can count 1, 2, 3, 4. 1, 2, no, that's different, that's different, that's not different, that's not different. That's wrong. You've got to look at the binding partners of those guys here, all right? So that's the chiral center, and the same would be here, the chiral center. And so our body as such is chiral. Where did it go? Okay. All right. It has this handedness. That means if I look at this hand here, if a little bit closer, please. Thank you. If I look at this hand here, and I put this on top, that's chiral. You see that? It's this handedness. Our whole body has handedness. So this would be cheating. This is not the right orientation. So you have these L amino acids that form proteins, and very often drugs, if you synthesize drugs for medical drugs, so they very often form chiral molecules, a mixture of both of them, and this is statistically distributed. There's the L form and the D form. And only the L form of that drug is being recognized by the receptors in your body, okay, to go whatever it's supposed to do, that drug. So, but the D form is not recognized. It doesn't do anything with the D form. But it's much cheaper to not purify it, just sell this whole mixture as the drug, and nevertheless, only half of it is active, biologically active for us. So now the patent, you have a certain name for this, now the patent runs out. What do you do, or what if you're a smart pharmaceutical company, you now purify. You have these 2 different enantiomers, they are called enantiomers, and they are, if they're in the mixture, it's called a racemate, a racemic mixture. And now you separate one out, and you only throw the one which is not active away, and now you have the active one only. Now you rebrand it, you give a new patent on it, you rebrand it, and you sell it as a new drug, okay? So now the patent will be staying much longer again, and you prevent this drug to be in this form, then be on the generic drug market. Nevertheless, the generic drug market can then sell the racemic mixture, okay? So this is how this works. So now you know we have structural isomers of here octane, 1, 2, 3, 4, 5, 6, 7, 8 carbons, and we have hydrogens, 3, 5, 7, 9, 11, 13, 15, 18 hydrogens, and these are structural isomers. I did not draw the hydrogens there. You know this, if there's nothing drawn, there must be 1, 2, 3 hydrogens, 1, 2, 3, 1, 2, 3, 1 here, 1 here, 1, 2, 3, 1, 2, 3. So you can save that. Now, in order to find out which of the following is chiral, what you go, for example, you go to this one here. Would that be chiral? This has 3 times the same, not chiral. This one has a CH3 here, not chiral. The moment you have 2 the same, can you forget it? You go here, this is hydrogen here, not chiral. All right? This one here has a CH3 here and a CH3 here, hydrogen here, and this rest here, not chiral. Okay? So I gave already part of the answer. Why don't you think about this and give me your answer, please? Four different things, not necessarily four different atoms, four different molecules, essentially, you could say. Combination of atoms. Okay, let's see. How are we doing with all the blood in the stomach? So at least the first one is not there. That's good. We decided that already, so you're paying attention. That's excellent. So now it's either B or C. But take a very close look at C and then take a close look at B. What do you see? Now we're talking, if you think about structural isomers, okay, structural isomers, would that be, and this be a structural isomer? Think about it very carefully. Now I confused you, but you will understand once you have discussed it with each other. Why don't you discuss this? It is important that you understand that. Very important. I don't want to be treated by a doctor who doesn't know what chirality is, okay? It's most likely that some of you will treat me. The older I get, the more is the frequency being in hospitals and doctors. Yes. Not right? You didn't? Okay. You got really tricked. I'm going to show you why. Now, if you compare this here already we established that it's not chiral. Isn't this the same? You just can put this up here. It's the same. Just because you write it like this, it's not, doesn't matter if this goes around the bend here, so you can also put it here. Okay? It doesn't give you a three-dimensional structure to begin with. So this is not chiral. So the possibility is pretty good, the probability is pretty good that this is chiral. So let's have a look here. This carbon, 3 the same, hydrogen, not chiral. This carbon, 2 the same, hydrogen, not chiral. This carbon, 3 the same, hydrogen, 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 not chiral. This carbon, 2 the same, not chiral. This carbon, okay, this has a CH3 group and this has a CH3 group, 2 the same, okay, not chiral. So how about this one here? This has a CH3 group here, then it has that C2 H5 group here, and then it has this whole group here. You see that? Okay. And here it has a hydrogen. So there are 4 different things around the chiral center, the chiral atom. And with this, here it is. This was 1, 2, 3, 4. This is 3, this is 1, this is 2, and this is 4. And with this, the answer was B, as you so rightfully had. So this, you need to know something like this, what the chiral center is and how to determine it. Probably will be on the midterm. There were some questions concerning how is it going to be. It will be multiple choice again. Will be only the things that you have discussed in lab, at homework, and the book what I gave you to read, the chapters, and what I discussed here in lecture from the last midterm, so from Monday morning when the last midterm was, till till Wednesday of next week. On Friday next week we have then a review session, and Monday you have your midterm, the second of 3. All right, so we have talked quite a bit about bonding. So we used that Lewis structure dot model, and then we sort of went into 3 dimensions. We used the valence shell electron repulsion model, VS-EPR model, so we could see how this would be coordinated in 3 dimensions. But remember, I put you through all this stuff to understand atomic orbital theory. And you are ready to use that atomic orbital theory now to have them bind. So what you could, for example, understand at this point is that if you have 2 orbitals on 2 different binding partners, if they overlap in phase, then they bind, okay? If they're out of phase, then they don't bind. So we will have bonding and anti-bonding molecular orbitals. So we now take the atomic orbitals and combine them to new orbitals, which we call molecular orbitals. And with this, we can say a lot about the bonding using the electronic structure that we get from quantum mechanics. All right? So let's do that. And we're going to talk about covalent binding, because this is the bonding what we talk about. The electrons have to overlap. If you have ionic bonding, there is no overlapping, because there's just electrostatic interaction. So covalent bonding is where the atomic orbitals form molecular orbitals. So we can have, for example, a 1s electron orbital. And so there's this green and red, so that has a pulsating, it becomes red and green and red and green and red and green, so the phase changes there. But, so if you have another one, so this would be, for example, hydrogen, you have them one atomic orbital and another atomic orbital. One is hydrogen and the other is a hydrogen atom. And now we bond it. We bind them together. So we have 2 orbitals, so we can't lose orbitals. We need to make one bonding orbital. This is obviously, if things bond, you always release energy, okay? Any formation of bond will release energy, and you go in a lower state, in a lower electronic state, in a lower energy state. This is the energy state. You imagine this is your energy scale here, and so this is the lower state. This is our molecular orbital, and it looks something like this, okay? So you gain energy by coming from these atomic orbital, individual atomic orbital states. Now they bond and go in the lower state and release energy. Now, but we had 2 atomic orbitals, and we have only 1 molecular orbital. We can't lose orbitals. So now comes the kicker. So we call this bonding a sigma bond. It didn't come the kicker, actually. That's the sigma bond here. And the bonding where you have constructive interference, that's the sigma bond. All right? S atomic orbitals, when they form molecular orbitals, they form sigma bonds. S for the Greek word sigma, for the Greek letter S, sigma, so that is very simple to remember, very easy to remember. Now, we have them now out of phase. So now we must make anti-bonding orbitals. So the anti-bonding orbitals, you can see, they have a node here. You see that? A node. So what can you remember from the atomic orbitals? You remember when you had a node compared to no node, which one had the higher energy? The node. And the more nodes you have, the higher you get in energy. Higher in energy, you get closer to zero. Remember, we have a large negative number down there, and then we go up close to zero. This is when we have totally removed that electron from the atom. So this is now an anti-bonding. It's also a sigma. This is how that looks. And this is in a higher state, higher energy state, compared to the initial state. These are the atomic orbital, here and here, and this is now the molecular binding and the molecular orbital anti-binding. And you see we have anti-bonding. We have here a star. The star stands for anti-bonding. Anytime you have a star, not necessarily, if you look at the sky, it has nothing to do with anti-bonding. But you have a star on this here, on a sigma, for example, or on a pi, then a star on a pi. Okay, I have to explain that. You have a star on a sigma, you have a sigma anti-bonding. That's all it means, all right? So let's look at hydrogen. Hydrogen has one valence electron and one electron to begin with, all right? It's a 1s1 configuration. There's one here and one here. So hydrogen by itself, if we would have the atom, it would be paramagnetic, would be magnetic, okay? Now, we distribute now each of this electron into the lowest bonding state, okay? And we follow what we follow there. We follow Pauli's principle and Hund's rule, essentially. But we have only one here, so it's no big deal. So this one goes in here. There it is, okay? So now we have two electrons in the bonding sigma molecular orbital. So we have a sigma bond. That's all it means. Now comes the next thing. You remember when we had these mesomeric structures where you have nitrate has 3 mesomers, where these alternating structures. We were talking there about bond order. Now I'm going to give you an even better definition about bond order. Bond order is the number of bonding electrons minus the number of anti-bonding electrons divided by 2. Now let's do that. How many bonding electrons do we have? 2 here. How many anti-bonding? 2 minus 0 is still 2, and now we divide it by 2, so the bond order for this H2 would be 1. So obviously it's possible. If the bond order is 0, then it's not possible. It's not binding. Let's go and have a look at this. So this, the individual hydrogen atom, is paramagnetic, so it shows magnetism. And if you have the hydrogen molecule, it's diamagnetic. Diamagnetic, doesn't show magnetism. So this is the bond order, BO. Never mind. Is the number of bonding electrons minus the number of anti-bonding electrons divided by 2. That gives you your bond order. So let's do this a little bit more with helium. So we have, if you have helium, has now, each of them has 2 electrons. In the atomic orbitals, there's one, there's upspin and downspin, upspin and downspin. So we form a bonding orbital. So we are still at the 1s, has to look like this. A bonding sigma orbital, and an anti-bonding sigma star orbital. So now we're going to fill these electrons in there. So there were how many? 2 were there each side. So we only can fill in 2 here, and we have to fill in 2 here. So what is the bond order now? Number of bonding is 2, minus the number of anti-bonding electrons is 2. 2 minus 2 is 0. Divided by 2 is still 0. What does this tell you? Does this molecule exist? No. Helium is monoatomic. It doesn't form molecules with 2 atoms. Okay? Monoatomic. So the bond order would be 0. Tells you right away. Okay? So let's go. We have now, this would be bond order 0. So this is the full shell, not the shell, the full period. This is the quantum number is filled. We go to next quantum number 2. And quantum number 2, we have now the 2s bonding and anti-bonding orbitals. I haven't drawn the individual ones here because it's the same than what we had before with hydrogen. We have one 2s orbital, one 2s electron, and another 2s electron from the other lithium. So we get 2 bonding sigma from the 2s, 2 electrons that are in the bonding molecular orbital, and none in the anti-bonding molecular orbital. What's the bond order of this? Does it exist? Bond order is 1. 2 minus 0 divided by 2 is 1. Bond order is 1. Does exist. Now let's look at beryllium. Beryllium has 2 valence electrons, and this is 2s2, so we have to distribute 4 electrons. So we put 2 in the bonding and 2 in the anti-bonding. What's the bond order? 0. Does beryllium-2 exist? No. Excellent. You are fabulous chemists. All right? You can predict all this stuff, if it exists or not. So let me ask you a question. We have a diatomic species, either hydrogen or helium or lithium. So I just made that up. I just told you that helium doesn't exist. But because the bond order is 0. Which one becomes more stable upon ionization? So we form an H2 plus, an He plus, and an Li2 plus. Let me give you that other overview here. Okay. So what you need to do here, you need to first determine what the bond order is before the ionization, and then you take 1 electron away, and you calculate the bond order again, and then compare it. So if it has increased in bond order, then it has become more stable upon ionization. So there are fractional bond orders. Remember, when you had these structures, these mesomeric structures, we had a bond order of 1/1/3 and 1/1/2. Okay? So there are fractional bond orders. So why don't you start thinking about this and give me your answer? Yes? Can you hear me? Yeah. There's a question and said, how do we know what are the bonding and what are the anti-bonding? So the bonding ones are the low ones. You fill them first, and then you go to the anti-bonding. So you count how many get you in the bonding, how many in the anti-bonding. You say the number of bonding minus the number of anti-bonding divided by 2. That was to be expected. That's why we have a discussion section. And so you know what is the bond order of this here when it is in the molecule. What's the bond order? We did that before, didn't we? It's probably in here somewhere. No, it's not there. Yeah, it's right there. Okay? And there's the other one. And helium you can do yourself. Helium and hydrogen. There's helium, there's hydrogen. Everything's right there. So it was 1. Now you take 1 electron away. How many do you have now in your bonding? 1. Minus 0 divided by 2 is what? 0.5. Exactly. Bond order 0.5. Your bond order has decreased now. It became less stable. All right? So why don't you discuss this with each other and see where you get, if you can give me a revised answer. There's helium-2 plus here. There's hydrogen. And there's lithium. Just take one electron away and then compare the bond orders. Ooh. Okay. So let's practice this together then. All right? Let's practice this together. So, hydrogen. Hydrogen has one here, the H has one here, and one here in the atomic orbital. Okay? We have two atomic orbitals, so we need two molecular orbitals. One bonding, sigma, and one antibonding, sigma star. Now we're going to start filling it from the bottom, from the lower energy up. So we fill this one in and this one in. So what's the bond order of this? It's 2 minus 0 divided by 2. Bond order is 1. Okay? What's the bond order of this here? So we have 2 here and 2 here. We are still in the 1s. Sigma, you have 2 minus 2 is 0 divided by 2 is still 0. What's this here? That's the same as this here, isn't it? So this is 1, 0, 1. Okay? Now, let's take an electron away. We take one electron away, so that means this is the ionized, so now we have the H2 plus, has one electron. H2 plus is 1 bonding minus 0 antibonding divided by 2 is 0.5, or 1/2, all right? Now let's take one away here, okay? So we have to take this away here. We take the highest one away, so this is gone. So we have 2 bonding, 2 minus 1 is 1, divided by 2 is 0.5. It went from 0 to 0.5. Before there was no bonding, and suddenly there was bonding. Now this one here is the same than this one again, because we're just in the next higher quantum number. So this is, we take 1 away. So this is 1 minus 0 is 1 divided by 2 is 1/2. So this was 1/2. So I even ionize it here for you. This is 1/2, this is 1/2, and this is 1/2. See that? So that means that the question that was, which of the following diatomic species becomes more stable upon ionization? So this became less stable, this became less stable, but this is not what I asked. I asked which becomes more stable. So this was totally unstable, and now it became stable. It had a bond order from 0 to 1/2. Okay? All right, the answer was this. You need to practice this because something like this will be on the midterm. So, the point here is that was easy. Sigma is easy. But now if we go up here to boron, carbon, nitrogen, oxygen, fluorine, and neon, we get p orbitals involved, atomic p orbitals. And you know atomic p orbitals, they have 3 different possibilities of orientation. They can be, if this is the x-axis, and this is like in your book, this is the y-axis, and this is the z-axis. So they have to interfere constructively, so the same kind of sign, positive to positive or negative to negative, would be constructive interference, and positive to negative would be destructive, and negative to positive would be destructive. So you have different possibilities now of bonding. In fact, you have two possibilities. They are the same with two different p orbitals, one each, one possibility each. And then you have one which is not the same than the other two. Why is that? So if you have, for example, the x here and the z-axis or z-axis, there's one atomic orbital here, this one, and this one. Forget the other ones, yeah? We're just looking at this one here. So this would be the pz, okay? That overlaps this way here. That means the interference happens here and here, okay? So that will make a pi bond, pi, okay? And then the other one that lays flat here, this is this one and this axis here. They are also parallel to each other, you see? This is this and this here. So they can bond here, and this is also called pi bonding. But now comes the third type, or the second type of bonding, where you have here along the y-axis. See, they are not oriented parallel to each other. They are oriented head-to-head or toe-to-toe. If I did this actually this morning, I was laying here with a student because they didn't understand that. So if you would lay here, and there's the head, and there's the feet, your center is in the middle, that's where the nucleus is. So the next person would lay here, the next orbital, that would be from the other atom, would be laying here with the head, so you have head-to-head, and the feet would be over there. Would there be constructive or destructive interference? Constructive. They would bind, okay? And this makes a sigma bond. Sigma, that's the sigma. So that's called the internuclear distance, the sigma bond. If now you have them laying, so that would be minus to minus. So this would be this. We would have to turn this around, minus to minus. Would that be constructive or destructive interference here? Destructive. It will not bond. It will do the anti-bonding orbital, okay? So you understand, if you have p orbitals binding to each other from two different atoms, then you have two different kinds of bond. You have sigma bond when the py overlap with each other. So this is in this axis here, the internuclear axis that are all lined up, the nuclei here. And then you have two pi orbitals for the pz and the px. They are laying parallel to each other, okay? So parallel is pi, and internuclear is sigma. And of course, then you have pi bonding, px bonding, or pi x bonding, and pi c bonding, and you have the same anti-bonding, and then you have the py bonding and anti-bonding. So how many pi orbitals would you have possible in the bonding? How many? Two. One when the px are overlapping, okay, and one when the p z are overlapping. So this you have two pi orbitals, and then you have one sigma orbital when the py's are overlapping, okay? Of course, you have the same number of anti-bonding orbitals. Let's have a look at this. So this is, for example, the px. It forms the bonding one. This would be the bonding molecular orbital. See, it has a node here and a node here, okay? But it's a node, it's not a plane, okay? And the anti-bonding, so that's the sigma 2p, is the anti-bonding has a plane here and a node here and a node here. Which one would have the higher energy? Anti-bonding, that's the whole point. The anti-bondings are always going higher in energy, the bonding goes lower in energy. So now you have, this would be the pz, and what else could it be? We have the p, what is that? That's the py, that's the pz. What else could it be? The px, the ones that are parallel to each other. Px and py. Okay, one orbital, the other orbital. My feet are the other part, okay? So I could also lay flat here. If I could levitate, then you would have the px, all right? So we have the bonding has one nodal plane, And the antibonding has 2 nodal planes. You see that? So high in energy. And then you have, again, the same thing for the px. So we have this would be the px bonding, and this would be the px antibonding. So I made here these signs on there, these signs are on there. Plus, plus means they are in the same phase. That would be constructive interference. Plus, minus would be destructive interference. You also seen it red. Red would be constructive interference. Blue, blue, constructive interference. Red or green, I can't remember, was green. Red and green would be destructive interference because they're out of phase. All right? So there it is again, sigma bonding. So that's our py's here. Wait. There's our py's. They formed that sigma bond. So now we have 2 more bonds that we form. And this would be the sigma antibonding. Now if we have the px or the pc, so the px comes out like this here, out of that frame, out of the screen. So you have 2 px's in each atomic orbital. There you go. So now you have the bonding pi x and the bonding pi c. How many electrons can you put in there? Total electrons? 4, of course. You have 2 here, okay, and 2 here. You can put in 4 in there. So because you also have the antibonding. This would be the outer phase. There would be antibonding. So you have a pi star x, and the pi star z antibonding. So you first fill those here, and then you fill these here. Okay? So the point is that p orbitals have different kind of bonding. They have sigma bonds. 1 sigma bond can have 1 sigma bond and 2 pi bonds. Okay? So let's just go through here with boron, where we start with the pi binding, the p binding. So boron B2 is 2 borons. Okay? So boron has how many p orbitals? So remember, the s we have done already. The 1s and the 2s we are done. Now we go into the p orbitals because they are filled. So there is no bonding. Now we go to the p orbitals, and we have boron has 1 in the p orbital, each of them. And so we put them, the pi orbitals, the bonding pi orbitals, 1 of them is each in there. Okay? Now, you have no antibonding sigma and no antibonding pi, because sigma you don't have at all there. And so what's your bond order? Is 2 minus 0 divided by 2, bond order is 1. Okay, exists. Now we have the next one, carbon. We have how many p orbitals? P electrons, let's say p electrons, 2. Okay, 2. So we have 2 from one and 2 from the other. So they both go in the bonding pi molecular orbital. The bond order, there's nothing in the antibonding. The bond order would be what? It says right there. it's 4 minus 0 divided by 2 is 2, okay? That's a double bond. Now the next one would be the nitrogen. The nitrogen has how many p electrons? 3. So it's a total of 6. So you have 1 each in the pi bonding molecular orbital and 1 in the sigma molecular orbital. Nothing in the antibonding. With this, you can 6 minus 0 divided by 2 is 3. Bond order is 3. That's a triple bond. And we know nitrogen has triple bonds. Okay? Now, something to confuse you a little bit is now suddenly the energy changes a little bit. Here is the break. Suddenly the sigma, if you come to here, the sigmas are a little bit lower lying than the pi. It's not a whole lot of difference, and I don't expect you to know that. I give you a scheme where you fill in your electrons. Okay? So I don't, but you should have heard that there's a break here, and that the sigma becomes the lower lying molecular orbital into the pi. So oxygen has how many? 4 p orbitals. So we have a total of 6 we can put in the bonding. First the pi, first the sigma and then the pi, all right? And then we have 4 is 8, so we have 6, so we have 2 then in the antibonding, because we have 4 twice 4. So this is 8, so we put 2, and now you have to follow Hund's rule with this kind of spin, parallel spin, here in the antibonding pi star orbital. Fluorine, so the bond order would be then 2, 4, 6, minus 2 is 4, divided by 2 is 2. Oxygen is 2. Yeah, double bond. We know oxygen has a double bond. Okay. Now we go fluorine. Fluorine has 1, 2, 3, 4, 5 p orbitals. So you fill them 6 in the bonding and 4 in the antibonding pi. You first fill them, and then you go to the next one. So 6 minus 4 is 2, divided by 2 is 1, bond order 1. Now, we come to neon. You have neon has 2, 4, 6 p orbitals. You go 6, so you need to fill in twice, 12. You have 6 in the sigma and pi bonding molecular orbital, and 6 in the antibonding molecular orbital. 6 minus 6 is 0, divided by 2 is 0, so it doesn't exist, all right? Now, you can tell me right away which one would be magnetic. Would be oxygen would be magnetic? Sure, it's magnetic. Unpaired spins, okay? Would nitrogen be magnetic? No. Now, why don't we do this? We fill in, if we could have the camera here on Karen, please. I think. All right, so there's Karen filling in nitrogen, bubbling, it's liquid nitrogen, very cool temperature, and liquid oxygen. Do you see something there with the liquid oxygen? Can you see something? It's blue, isn't it? It's nice and blue. Oh, this oxygen, I gotta get a little oxygen. Oh, excellent. Wonderful oxygen, I feel refreshed. Okay, it's blue, and I explained to you at one of these lectures, I talked to you about this, I think, before, that it has to do with the electron spin. One flips around, back and forth and back and forth. So it absorbs light, gives off light, absorbs light, gives off light. That's what makes it blue, okay? Now, we have a magnet here. If I can have the other picture, please. We have a magnet here. It's a huge magnet. And so if we pour that liquid in between there, the one which is paramagnetic should be kept in between the pole shoes. So let's do nitrogen. It's a beautiful picture. Nothing, niet, nada, nichts, okay? So it doesn't, so it is, and this is what we predicted. Nitrogen is not magnetic, all right? So let's do oxygen. You said all it would be magnetic. Let's see if it's true. There's oxygen. Now, see that? Now watch very carefully when only the gas is there. Even the gas behaves magnetic. Of course it should be. See, it's still there. The gas, right there. Let's do that again. So you could predict. You are absolutely marvelous. You can predict now if it's paramagnetic or diamagnetic, right? Given that you know what diamagnetic is. Okay, so we are not done yet. I have to show you one more thing here. Thank you, Karen. Look at the gas. Look at the gas. Let's keep it on. Let's keep it on. I have 2 more minutes from you. All right? Thanks. If I could, let's go back to the lecture. No, we are not done. All right. So what you do, for example, these are some compounds, they have very small changes in magnetism only. So you have to have a very sensitive measurement in order to detect this. So you have a Guy balance, for example. You have a balance here, and there you have a glass tube, and you put your sample in there, and then you have an electromagnet. You switch that on, suddenly it pulls it down a little bit, but it's so small, the changes at times, and this is called measuring the magnetic susceptibility. And this is how this is done, how you can characterize semiconductors and other things, and low temperature or high temperature semiconductors. So, and then we have a question for the next time, and I wish you a good weekend.